Okay, well, thank you for the invitation to be here. Well, my first time, actually, in this part of the world, by which I mean Italy. Okay, so everything I talk about today is joint work with Dave Rose and Paul Vedder. Hi, Paul. Here somewhere. So before I sort of start saying anything mathematical, let me give a little asterisk. So you know, I'm hope this doesn't upset anyone, but the title could be a little bit of a misnomer because we won't be talking about roots of unity at all. So we don't work at so when people talk about the Turaev-Viro invariance, you have to fix a root of unity, and then you perform some big computation associated to a three-manifold, and then you get an invariant. To categorify that, you would expect you want to categorify the coefficient ring, the ring of roots of unity, but we're not going to work in that setting. But we don't have to because we're categorified, so things make sense sort of anyway. So they at least won't be discussed in the categorified situation. Okay, so a little outline of what I'm going to be talking about. So I want to give sort of a big picture, some context of where our construction lives in relation to things that we've heard about already in the conference and workshop, namely skein, lasagna, modules, and related things. Then I want to recall a sort of naive or underived. So I'll recall something called the Barnathon construction, which is like a three-dimensional version of the skein lasagna. So it occurred earlier in history, and it's like a three-dimensional version of skein lasagna. The main the main thing that sort of we're working on is making that into a derived construction. So lasagna and Barnathon skeins are not sort of derived enough for some kind of things we want to do. So a lot of the hard work or technical work is in making these things derived. And then sort of at the end, I'll explain in what sense that's supposed to give a categorified Turaev-Viro. Okay, so this big picture, the context. So I want to mention just sort of briefly, I'm not going to be talking about skein lasagnas in any detail. I just want to recall some of the main features. Oh, by the way, throughout this talk, all manifolds are, compact, smooth, oriented. I won't always write those adjectives. So, but what does skein lasagna do? It associates to a pair consisting of a four-manifold and a link in its boundary, a vector space. I'm also going to be suppressing gradings for as long as I can manage to. So to a pair of four-manifold and a link in its boundary, you get a vector space. From this construction, you can actually also extract out a category. So for a three-manifold and a collection of points in its boundary, so my collection of points, let me call it B, 0. So given a three-manifold and a collection of points in its boundary, I actually get a category that maybe you guys talked about, maybe you didn't. And so over here, I'm going to have some relevant pictures. So objects in the lasagna category of a three-manifold are tangles in that three-manifold. So here I've drawn my three-manifold as a ball, and I've chosen 4 points in the boundary of that ball. Now an object of my lasagna category will be a tangle in that ball, and a morphism between two such tangles will be a covertism or a lasagna filling. And then these can be composed because they're basically cobordisms with corners, and that gives you the composition of morphisms. So that makes this into a category. One of the things that I want to say as sort of motivation for like why we want to derive, why we want derived versions of things. Why do we want to make a hard life even harder? So we have the Skane relation that is extremely useful in it's part of the definition of Kavanagh homology here. It's extremely useful in computing Kavanagh homology. So there's this Skane exact triangle that, says the Kavanagh complex or the Kavanagh chain homology of a link, and if you switch, I think we all know what the Skane relation says. Let me just sort of say in words, though, that the Skane relation here, the Skane exact triangle, involves, so what we normally call the Skane lasagna module is only the degree 0 part of something much even harder, this sort of like homology of this blob complex that maybe you've heard of. So the Skane exact triangle involves not just the degree 0 part, but all degrees of this blob complex. So there is a Skane exact triangle that you can write down. For example, here I have an object of my category associated to the 3-ball, and I know, because this is a 3-ball, that there's a relationship between that object and the guy with the crossing change and then the identity. But if you had a more general 3-manifold and you wanted to ask for that relationship, it becomes this sort of Skane exact triangle, and it involves all blob degrees, sort of the whole entire blob homology, which is not something we want to talk about right now. So the point is that this is very hard. And maybe what I'm going to suggest is also hard, but I think it's maybe less hard. Another problem is that the homological degree in the Kavanagh chain complex, or in the Kavanagh homology, doesn't communicate with the blob homology degree. They're two distinct homological degrees. You've taken Kavanagh homology, treated it as a bi-graded vector space, and then fed it into a construction that produces a complex and then takes homology. So you fed a homology into a thing that produces a homology. And I don't want to do homology twice. I want to do homology once and only at the very end when you force me to. Okay? So I want a complex which is defined at the chain level, and then maybe at the end you can sort of hope, if you're very optimistic, that what you get is like the target of a spectral sequence starting here and then ending up somewhere nice. Okay, so I'm going to erase this because I want a little diagram. So I want to ultimately, I think it would be great to have a derived version of the Skane lasagna construction, and that is not what I'm going to talk about today. What I'm going to do instead is I'm going to consider a 3-dimensional version of the Skane lasagna construction. Because, okay, so that's called the Barnaton construction. And what the Barnaton construction does, or is given a 3-manifold with the link in its boundary, you get a vector space. And you can turn this construction also into a category. Given a surface and a set of points in its boundary, you can convert this into a category. And the picture for this is a little bit easier to draw and digest. So here it is. So I've tried to draw a surface. Okay, but anyway, so let's say, let me back up for a second. So objects in this category, so I fix a surface and I fix a number of boundary points. In this picture, my boundary points If you can see them, there's two of them right here. And objects of my category are tangles in my surface. And I say the word tangle, but they're not allowed to have crossings because they're embedded in my surface. So there's one object in this category. Here is a second object in that category. And morphisms between those two such objects are given by three-dimensional. Maybe we don't call them lasagna fillings anymore, but I'll call them three-dimensional lasagna fillings in this thickened surface. And the thing that's worth pointing out here is that the meatballs in this lasagna they get replaced with dots. So instead of drawing them as meatball, in the skein lasagna construction, you have these meatballs, and what are they? They're really embedded. They're really embedded four balls that intersect the surface and with some link in the boundary, and then you can decorate the meatball with a Kavanagh homology class of the link at the boundary. But here in 3D, our balls are going to intersect our surfaces only in unlinks, and so we can decorate them with Kavanagh homology classes of the unlink. So we draw them as dots because there's only one non-trivial class of the Kavanagh homology of the unknot. It's X. So we draw it as a dot. So now instead of the meatballs being drawn as meatballs, we just draw them as dots. And then there's some relations that may look familiar to you if you've seen them. There's no need to really spend much time with these, but there's some relations that just come from looking at the cobordism maps in Kavanagh homology, coming from looking at very basic maps from the empty into the unknot and then back. So you get these relations. So the classical Barnaton relations. This one here is called the net cutting relation, and it comes from looking at if you want, you can think of it as coming from, look at this cobordism. It's a cobordism from the empty link into the unlink of two components, and you ask yourself, where does it send? So the Kavanagh invariant of the unlink is just the ground ring. Where does this cobordism send 1? Well, it sends 1 to x tensor 1 plus 1 tensor x. And so turning your head sideways gives you this relation. Okay. So this is the Barnaton construction. And I am asserting that we want to derive both of these things, and this one is easier, so we'll start there. And maybe the main or maybe only motivation I'll give you for why you care about why we want to derive things is we want a better way of understanding how the skein relation, which is a relationship between Kavanagh complexes, how that can be sort of baked into something like a lasagna theory. Okay. And maybe I'll say one more thing before moving on from this big picture or context. Over here in this column, we have theories that are they are categorified, but they're 2 plus 1 dimensional. And over here we have theories that are 3 plus 1 dimensional. And the guys over here want to be a categorification of the Crane-Yetter TQFT. Because, I apologize, maybe I ought to say more about the Crane-Yetter TQFT, but I don't want to. Let me just sort of say that if you have heard of the Crane-Yetter TQFT, this guy wants to be a categorification of it. The thing associated to a three-manifold wants to be like the skein module of that three-manifold, or the categorified skein module of the three-manifold. But you have too many objects because your construction doesn't know about the skein relation. And this guy wants to be the one-dimension lower version of the Crane-Yetter construction, which is Turaev-Viro. So this guy wants to be a categorification of Turaev-Viro, but it doesn't become one until you derive. This guy wants to be a categorification of this Crane-Yetter TQFT, but it isn't, but it ought to become one once you derive. Okay? So that's the sort of philosophy. These guys are almost the things that we had been looking for all along, like categorifications of Turaev-Viro and Crane-Yetter. It's just that they weren't derived enough. And I hope to convince you of that today somehow. Okay. So that's the big picture. Before I talk about how to derive the Barnaton thing, I would like to give you the right way of thinking about Barnaton that will make it easier to derive. So, you know, the whole game is to write the old thing in a way that it becomes crystal clear how to do the new thing. So ultimately, I would like to describe this invariant from like a handle decomposition of my three-manifold. So let me talk about how the Barnaton construction behaves under handle attachments. And then by deriving those, we'll get the sort of derived thing, morally speaking. Okay. Are there any questions? If at any point I can like answer a question or be more clear, please stop me. Okay. So I just want to spend a second talking about the Barnaton module or whatever of the three-ball. So I want to understand the Barnaton construction handle by handle. So we have 0 handles, we'll have 1 handles, we'll have 2 handles. And we're not going to talk about 3 handles because, well, yeah. So maybe I'll say that now. We're not going to talk about 3 handles because we just aren't. We don't know how to do the derived thing yet. We're still working on that. But that's okay. So we're describing our 3 manifolds as built up out of 0, 1, and 2 handles, which means there's a little sphere at the end that we don't know how to cap off. But that's not an issue for invariants of 3 manifolds. Okay, so let's talk about the 0 handle, the 3-ball. Okay, so if I start with a 3-ball, so I want to understand the Barnaton module of a 3-ball, and what I have to choose a link in the boundary. So here's my 3-ball, and I'll just draw my link as a 2-component unlink. Well, inside this sort of Barnaton module, I have any cobordism that any surface bounding that L that I've chosen in the boundary, and that surface might carry some dots. But then we use those relations to simplify as much as we can. So the net cutting relation allows us to sort of separate the bit which bounds this disk from the bit that bounds this disk. And so everything is a linear combination of something bounding that guy and something bounding this guy. Using the net cutting relation more if you need to, the only so the vector space here is 4-dimensional because you have just a pair of disks, and they might have 0 or more dots on them. So this is the sort of hopefully familiar thing. This is just the Kovanov invariant. So as a vector space, it's the Kovanov invariance of the 2-component unlink. Here's the class 1, 1, here's the class x1, here's the class 1x, and here's the class xx. Okay. Should I say more? Oh, I'm sorry. I forgot to write that. Yeah, the double dot for me it squares to 0. Yeah. Yeah, sorry. Okay. Yeah. So it's yeah. That's right. This is all meant to be occurring inside a embedded 3-ball in your 3-manifold, oriented 3-ball in your 3-manifold, And here you have a compressing disk.
So when you do this, you will keep a closed surface inside the three-manifold possibly.
You might, yeah. These surfaces don't have to be closed. In the Barnaton sort of skein module, you can have closed components. That's fine. Okay.
In Barnaton, you evaluate always the closed surfaces here. The question is about evaluation of, for example, an embedded torus inside the three-manifold. Abstractly, it is evaluated, but
well, not always. No, I mean, if your surface is T2 cross I, or if your three-manifold is T2 cross I, and your torus is the, you can't embed that. You can't evaluate that. Yeah. Yeah. So not every closed surface will evaluate to a scalar multiple of the empty diagram. It might be essential or something. That's okay. Okay. So now that we understand zero handles, let's understand one handles in this Barnaton sort of invariant, Barnaton skein of a three-manifold. I want to draw a little picture here. So let's spend some time with this. So here well, I guess half of you are on the other side of the room. So here what I've done is I've drawn a zero handle, I guess a zero handle is this big sort of blocky box thing. And we're attaching a one handle, a 3D one handle to it on one side. You should imagine, or from this picture, the link that I have in the boundary of my three-manifold consists of these these blue arcs here, together with arcs that run along the one handle. So the link in the boundary is the union of this mess that I've sort of highlighted in red. Okay? Now you have so suppose you have a surface inside that three-manifold that bounds this L. You look at how that surface hits the one handle. It hits that one handle in some surface, but that surface will be a cobordism. I've only drawn part of that cobordism. And the point is that because I've connected this sort of guy and this guy with the one handle, any cobordism which I sort of plug into this foot of the one handle, any cobordism that I plug into this foot of the one handle, up to isotopy can be dragged around and it pops out the other side upside down. So in fact, that's sort of everything that we need to know about the one handle. So the claim is that for the Barnaton module of a three-manifold, so let's say the three-manifold is presented as a zero handle plus a bunch of one handles. The claim, so let's say that there's G one handles, I guess. I don't know, is that a good letter? The claim is that this is equal to or isomorphic to, you take the Barnaton module of the zero handle itself. Oh, and sorry, and then there's a link. The claim is that this is isomorphic to the Barnaton module of just the zero handle itself. But where the link that you put in this boundary is potentially complicated. So the link that you put in its boundary is the union of a bunch of things. So first off, I'm going to put T0, where the symbol T0 represents everything. So T0 is meant to be L minus a neighborhood of the attaching feet. So in this picture, T prime is the sort of exterior, okay? So union. And then inside the neighborhoods of the feet of the one handle, you can plug in any tangle that you like. So I've run out of space. I keep looking for an eraser, but sorry. Let me write this down here. And then you plug the holes of, you plug the sort of neighborhoods of the feet of the one handle with some further tangles. And so I can push all the interesting bit of surface away from the one handle. And so I can just think of I can arrange that that lasagna filling or whatever, the surface meets the one handle only in like an identity cobordism, so that you'll see the same tangle coming into the right foot as you see coming out of the left foot. So you do this, you take a big direct sum over all tangles T1 up to TG. And then you mod out by the relation that we said, which is that any cobordism that gets applied to T1, sort of you can apply the dual to T1 dual, and those two guys should be sort of equalized or co-equalized. So here it is. Here's the example and maybe the precise. Okay, so if you start with, if this is the diagram representing your, let's say you have a single zero handle that I haven't drawn according, so I have a single zero handle and I have two one handles. I've got the A one handle and the B one handle, just drawn and then I've got a tangle T0, which is the sort of describing the link that I prescribed in the boundary of my three manifold. Now what I do to get the Barnaton-Skane module of that three manifold with that link is I do a direct sum of all possible ways of plugging in the sort of disks here with some tangles. And whatever tangle I put in this foot should be dual to the tangle that I put in this foot. And so there's only two choices I could make. And here they are. So I take the direct sum of these two pictures, and now what each of these pictures represents is that it represents B3 with some link in its boundary, and I've just told you how to think about the Barnaton-Skane module of that. So you take the Barnaton-Skane module of this, which is some four-dimensional vector space, the Barnaton module of this, which is some four-dimensional vector space. You add them together, and you oppose a relation that says any cobordism map that you could have applied here, well, you could have applied the dual of that here, and you want to equalize those. You mod out. Is that cool?
The original L is that picture with
the original L is exactly. The original L is this picture together with bits that I haven't drawn and sort of can't draw, which go around the one handle. Yeah. So these dudes are not part of the link L, but they are part of they're part of a surface that might come in and go through the one handle. Yes, that you can arrange also that your surface, any closed, using the net cutting relation, any bit of surface, any sort of, in principle, you could have a bit of surface that goes through the one handle and intersects the neighborhood of the one handle. In principle, you could have a bit of one handle that comes and intersects you could have a surface that comes in and intersects the one handle like this. But such a surface, using the net cutting relation locally, can be broken and pushed away from the one handle.
And you're assuming that what the links look like when they go through the handle, that there's, I mean, there are many different ways you could connect them. You can put a link through that one handle.
I'm assuming that everything that touches the one handle sort of is trivially propagated to the other side. Yeah. And I can assume that just by pushing everything away from the okay. Okay. So this is an example of the one handle. And here's maybe let me give you a picture that sort of represents more algebraically what's going on. Okay, so this is maybe a bit of a schematic, but I think it's a useful sort of schematic. So I've got my 0 handle with the attaching feet of its various one handles that we're going to be attaching. And here I've got the one handles that we're attaching. Everything in sight can be thought of, everything in sight can be thought of as a module, and then we have then we have the link, which I haven't actually drawn in this picture at all, just because I think it would clutter up the, but you should imagine there's some blue curves in this picture which represent, the link L that we've prescribed. Everything in sight is a module of an appropriate Barneton category, because you can, this process of plugging holes in where the feet of the one handle go, that turns this Barneton construction of B3 minus some disks with the tangle T0, it turns this into a module for a bunch of Barneton categories. And the one handle guy is also a module. It's a module for 2 copies of the Barneton guy. And what we're doing when we build this sort of Barneton module of the 0 handle plus its one handles is we're doing a tensor product. We're sort of taking the module associated to one handle, taking the module associated to the 0 handle with its attaching feet for the one handle, and we are tensoring them over some intermediate thing. And then what that tensor product does is it says, well, any cobordism which could have been glued here hits this one handle where it becomes equal to upside down itself, and then it is equal to what hitting there. So the relation that cobordism slide with an upside down is exactly occurring inside the one handle. Okay. So this is the picture of the one handle attachment that's going to be easy to derive, because all you do is you put a superscript L over this, and you call it derived tensor product, and you're done. Question?
So, does it follow from this picture that if you're in this situation, so if 0 handles and 1 handles but no handles of higher index,
Not yet.
the module will be finally generated?
Yeah. Yeah, exactly. Well, finally generated with no 2 handles. If you only have 0 and 1 handles, yeah. Yeah, question?
So after you derive it, is it still clear that you get any value?
Well, let's talk about the derive thing. Yeah, it's a great question. Maybe I'll answer that once we talk about the derive thing. In fact, this picture is a picture of the derive thing, and I want to skip it because I want to talk about 2 handles. So I'll come back to this derived one handle here in a second, but ask that question later, and I'll hopefully answer it. Okay. Now that I've drawn that picture of you have a module associated to a handle, and then attaching the handle is just tensor product, now I can start to be a little bit more hands-off about how these things are defined. I just say, okay, so what this picture represents is, okay, I take my 0 handle plus its 1 handles. So 0 handle, 1 handles. Now I draw a curve in pink, which represents the attaching circle of a 2 handle that I want to do. Okay? I draw a regular neighborhood of that attaching circle. So I've shaded everything else except, so I have this pink curve, which is the attaching circle of my 2 handle, and the neighborhood of that is this sort of white ribbon. The claim is that the Barneton category of, so you might have a bit of link also, which I haven't drawn, but maybe ought to have. you might have a bit of link in this picture. But this picture by itself is a module over the category that we associate to the annulus, the Barnaton category of the annulus. Just by taking a picture drawn in the annulus and then plugging it into the neighborhood of your attaching circle. So that part is just plugging in holes, but now instead of the holes being neighborhoods of S0s, they're neighborhoods of S1s. Okay? Then the tricky part is, well, you have to take that module and tensor it with something that is associated to the two handle that does the sort of two-dimensional version of this, okay, well, when you put a surface into the one handle, it's got to come out upside down on the other side. Well, there's a two-dimensional module that describes whatever happens when you close up in a disk. And this two-dimensional module is more or less what was completely described by Ciprian Manolescu and Ikshu Nihilev. But whatever that is, and what it is isn't actually super important for my talk today because it's not going to enter into the derived story very much. But let me write that the sort of the module associated to the two handle itself to this like three-dimensional, well, okay, what they do is they describe the four-dimensional two-handle attachment, but the same exact story applies to this three-dimensional two-handle attachment. This was basically completely described by Manolescu and Nihilev. And I'm tempted to tell you more about it, but I think it would be a distraction, and we're not actually going to use it later, so let me skip that. If you're curious, maybe talk to me afterwards. This one will not be finally generated, exactly. Yeah, for example, you could just take S2 cross I. That will be locally finite dimensional, but still infinite dimensional. Maybe second homology class mod 2. Yeah, is it mod 2 maybe? But yeah, basically for this Kavanagh homology version, I think you get maybe a grading by second homology mod 2 because you can pipe two parallel things together with the net cutting relation. And the surfaces that the lasagnas are orientable, but we don't actually choose an orientation. Yeah, sorry, okay. Yes, for the GL2 version of this story where you have oriented, where the blue curve, the L's here are oriented and we're careful about yeah, so in the GL2 version of the story, you would have like these GL2 foams as studied by Blanchet, and then yes, you would be graded by H2 of your surface.
Yeah, if you two handle is cancelling the one handle, then you see from the Barnaton relation that
They cancel?
everything disappears. So.
Can you see directly that the two handles and the one handles cancel when they should?
No, I mean you are.
Is that the question?
Generators when you put a one handle and especially a two handle.
Yeah.
So we expect the same vector space as the initial one.
I think it's easier to prove that this construction recovers the Barnaton construction, and so the two handles must cancel the one handles. I don't know of a cute way to see it directly. Paul, did we? In the derived version, it's maybe easier. I don't have an argument.
That's my question. For this, do you need the derived version, or is it?
They ought to cancel underived. The underived one handle and the underived two handle ought to cancel. But I don't know. I don't know of an easy way to see that. other than just proving that this description reproduces the Barnaton invariant of the three manifold, which we know is an invariant. Okay. So that's maybe all I want to say about the underived Barnaton construction. So let me start talking about how to derive this thing. So derived one handles, derived two handles. So I want to say that we don't do anything different for the zero handles. We still have the Barnaton construction for just the B3. So given a ball with some closed multi-curve in its boundary, the vector space associated to that will be just the same as it always was. For one handles, what we need to do is we need to replace this one handle thing. Well, it was a module over the Barnaton category of a disk with some prescribed boundary tensored itself. So the one handle guy is a module over, one of them has an opposite because of this cobordisms becoming their orientation reversal, or their reflections, or rotations rather. And maybe, again, to be completely precise, remember that we have this, ultimately we have this link in our three manifold, and that link is going to intersect the attaching, or a neighborhood of the attaching circle for the one handle in some points, so let's draw those points. But anyway, this one handle module is a module over this thing. And what we do for the derived thing is we just replace this by a projective resolution. So that this tensor product becomes derived tensor product. And then a picture for this was actually up here. So this is a sort of schematic. So the one handle describes a module over two copies of the Barnaton category in the following sense. You can plug one of the feet with an object of the Barnaton category. You can plug the other foot with a different object. Then that becomes a two-sphere, which is the boundary of B3, and you know how to sort of evaluate closed multi-curves inside B3, on S2 using the zero handle stuff. So this is some vector space associated to a pair of tangles S and T, and every single one of these things is a vector space associated to a pair of tangles. You take a pair of tangles and a disk, glue them together, and evaluate that using the sort of Barnaton construction on B3. So you take a big direct sum over all possible ways, you do the bar construction. So you take a direct sum over all sequences of tangles T0 up to TR for any R. You do the same thing for S's, S0 up to SU. You take a big direct sum of all of these things and you put a differential on it that is the usual bar differential. So each adjacent pair of spheres has a sort of multiplication map that sort of pairs S3 with S3 dual, or S2 with S2 dual, and so on. So you do this sort of bar construction, and that gives you your projective resolution. This is just a formal standard way of getting from like a module to its projective resolution. One comment is that if you ignore one of these actions and just remember the other, so this thing is sort of already projective over one of the copies of Bn, but not both. So in fact, you don't need to do a projective resolution with respect to like both feet. You only need one. So there's a slight simplification where like this complex is a little bit bigger than it needed to be. I did 2 bar complexes and I could have gotten away with just 1. But anyway, that's the derived one handle. You guys have actually seen this before. If you've ever thought about stable homology of torus knots. So there's this chain complex constructed by Brzezinski. So here's a little fact. So if you take, so let me just take a local picture. So I have the 2 feet of the attaching circle of some one handle, and I've got a bit of link in the exterior. If I then glue the sort of one handle to this, the derived one handle to this, this will reproduce this Brzezinski projector. That some people denote in this way. So it's the projector on 2 n strands where here n is 2. And the 0 means it's a 3 degree 0 object. So there's no blue strands that run all the way from this A to that A. So this is called the Brzezinski projector. That's sort of neither here nor there if you haven't seen this object before. But if you have seen this before, then it maybe hopefully demystifies a little bit what this thing is. So that's the one handle. So the 2 handle, there's not much that one can say about this in a small amount of time. But let me just say that the one handle was almost trivially obtained. The derived one handle was almost trivially obtained from the underived one handle just by inserting the word, like just by doing projective resolution. But the 2 handle is much more complicated. Because the category that you associate to the annulus is more complicated. So the sort of derived category of the annulus is more, well, it's a DG category, so it's much more complicated. Than the sort of naive version. So that when we do this sort of 2 handle attachment, is also more complicated. So 2 handle attachment is a derived tensor product over the category that we associate to the sort of derived version of that category that we associate to the annulus. Okay. So this is much more complicated. So in the underived version, you had a much simpler category here. And you might have expected the derived thing to just be derived tensor product over that simpler category. But no, the right thing to do is to take the derived tensor product over this new category that you defined. And so let me talk for just a second what this category is. So how do we get from these spaces or complexes or whatever associated to 3 manifolds to categories? Well, remember this construction that we do is we take surface cross I and look at, so what is this category? So this is what we're going to call DGABN. So the ABN stands for annular Barnaton category. So the objects of this category are up to isomorphism in whatever category this is. The objects are just going to be concentric circles embedded in that annulus. So I'm going to, so there's, I'll call them E and E squared and E cubed and so on. Just some number of circles wrapping around the annulus. And how do I get Hom? What's the Hom space from EK to EL? Well, that should be the derived Barnaton sort of complex now, associated to the annulus cross I, and with this link in the top or the left part and this link in the right part. So you take the link that you put in the boundary of this thing is EK cross 0 union EL cross 1. And then you evaluate that according to the rule. So you evaluate that according to the rule that we had for the one handles. So let me continue over here. The Hom space between these two things is so it's this Rzansky projector thing, or this derived one handle guy, closed up and evaluated in the plane. So this is some infinite complex, and that's the complex of Homs between these two objects in that category. So zeroth cohomology of this is just what it was before, but now you have all kinds of stuff in like negative cohomological degrees. So you get a much more interesting category this way. So when you do this derived tensor product, you get something kind of wacky, but it is what it is. So this might, I think I'm running out of time. So, but you get a similar story. So given a two handle that you want to attach, we show that the sort of chain complex associated to this picture is really a module over this sort of derived Barnaton category of the annulus. And then we tensor with this module that maybe I can tell you what this module is. This module is pretty easy. So the module associated to the two handle, that's this thing. Well, it's going to be a right module over this category. And so a right module over that category is a functor from the opposite thing. So take the derived Barnaton category of the annulus, op, and this is supposed to map to complexes or vector spaces. And what this functor does is it just takes an object of that category, so some number of concentric circles, and spits out the Kavanagh homology of that object, thought of as a link in R3. So these are always unlinks, and so this Kavanagh homology is just always a tensor product of two-dimensional vector spaces. So this is like a very easy functor to describe. It's just that it's leaving a very complicated category. So when you do this derived tensor product, you get something kind of heinous. I'm running out of time to tell you how this is all connected to Turaev-Viro, but let me do say something about that. That's what we're here for. I guess, are there any questions while I'm erasing? About invariance? Well, yeah, okay, so to prove that you actually get an invariance of 3 manifolds, you need to check handle cancellations, handle slides, invariance under handle cancellations and handle slides. So I can't say more than we can prove those things. I guess your question is probably how do you prove those things? Okay. It's complicated. Okay. So what does this all have to do with Turaev-Viro? So, gosh, I'm like really out of time. So to prove that this is a categorical analog of Turaev-Viro, we need the right model for Turaev-Viro. So the model that we're all sort of familiar with, maybe because it's easiest, or if we're familiar with Turaev-Viro, the model that we've probably seen before is the state sum module that involves state sum model that involves 6J symbols and thetas and whatnot. That's actually not the easiest one to work with from this point of view. The right model to use here is actually due to Justin Roberts. Paper is Skane. Well, if you look up Skane relation or Skane theory and Turaev-Viro, you'll find it. It's a really beautiful, wonderful paper. I recommend you read it because it's the easiest way to get into Turaev-Viro if you're a link not person. Okay. So maybe just in like very, very quickly, what I can say is in this description of Turaev-Viro, he starts with a Hegardt description, Hegardt splitting of your 3 manifold, which is basically the same thing as a handle decomposition. Okay, so let me just draw a simple Hegardt diagram of something that we might care about. I'll just tell you what Justin Roberts does to it and then why it looks very similar to what we do. And that we'll have to do for now. So there's a Hegardt diagram for a lens space. And the invariant, what Justin Roberts would do is he would push the red curve outside of the, this picture slightly so that it now links the blue curve. He would color both of these with something called a Kirby color. And then he would evaluate that in the plane using the sort of Jones-Kaufman bracket relations. And let me not define what those relations are or even what the omegas are, but I can tell you that what the omegas are is they describe an adjoint to the linear map given by the two-handle thing. So omegas, what they do is, so you have this vector space associated to the annulus now. So this is the skein module of the annulus. In this context of, here we're working with SL2. And you have a map from the skein module of the annulus to the skein module of R2, just given by forgetting the whole of the annulus and then plugging in. This map, it's a map between finite dimensional vector spaces. It has an adjoint. So this is a finite dimensional vector space with an inner product. So it has an adjoint. It's in fact a biadjoint. And it sends 1 to this special element Kirby. So what that means is that the Kirby guy is the thing which multiplication by it realizes the attaching of a two-handle. So the Kirby guy is the element of this thing associated to the annulus. So it's an element of the skein module of the annulus, and multiplication by that element realizes this sort of two-handle module. And then there's a further property that when you take... Oh, yeah. Sorry. Thank you. And I'm sorry for going over. Let me wrap up in just 20 seconds. There's a further property that this Kirby element satisfies, which is that this is equal to this through degree 0 projector. If you normalize correctly, this is the through degree 0 projector. So actually what Justin Roberts' description is doing is he's telling us, okay, so to each red curve, which we think of as representing the one handles in our handle decomposition, we attach a through degree 0 projector. And then to each blue curve, we associate this guy omega, and multiplication by omega represents like the turning on the disk relations. So in this context, what I ought to say is that we have an object of our annular category, which is we call the derived categorified Kirby, that has a similar sort of effect. So I'll stop there. If you have more questions, please feel free to stop me now or later today, or I'm here all week. Thanks, guys. Yeah. Yeah, so there's no decategorification statement. That's right. So the title is maybe a misnomer. It's a categorical analog of Turaev-Viro, but with no actual decategorification. Well, yeah, okay. So in particular, we have no proof that the invariance of three manifolds that arises this way would be locally finite dimensional. So it might associate infinite vector spaces to, yeah, so.
So it just has the same flavor as Robert's stuff, but it's not actually the same.
That's right. It has the same flavor. That's right.
But you have this adjunction.
Yeah. So that's right. So the point is that here in linear algebra, the decategorified world, we needed this to be a finite dimensional vector space in order to build an adjoint to this map. That's really why you need roots of unity, and only why, pretty much, is this one place. Because the adjoint to a map, needs to send 1 to a finite sum of things. And that sum is infinite unless you specialize to a root of unity. When you categorify, you can build adjoints to functors even in situations where you have, like, categories that you can build adjoints to functors. They might be big, but that's okay. You can formally adjoin big things to your category if you need to.
Can't you see your adjunction at the level of the Grothendieck group of your category?
Well, I guess the point is the Grothendieck group of our category might be 0 or something. can't say much about, or like even, yeah. I mean, I guess you could just take the growth in D group of what we do, but we can't prove, and it's maybe even likely not true that you get a non-trivial statement. I don't know, we haven't.
Let's say your manifold was a surface times S1. Is there a tractable way to carry out the formula you described for one handles with a category associated to lengths when your surface is closed, lengths in that surface, and make a tortoise of the surface times I?
Yeah, so it's a great question. I think like in general, having tractable computations is still sort of difficult. And I guess having a surface, well, okay, so having a surface cross S1 maybe minus a ball. So I can sort of show you a picture of what you would want to compute, but just the computation of that thing might be tricky.
Yes.
If you cut a free manifold along some arbitrary surface, do you get a derived tensor equation?
I mean, you would expect that, but that's maybe not something I can. That type of question is a great question, but maybe in the future. Yeah, so you would want these derived invariants to, like, the reason for deriving them is because you want to have nice cooling properties and whatnot. But let me answer, and let me just say probably, but that's not something we proved.
So in the Roberts formulation, that's a length in the free sphere. In your formulation, you want it to be like a length in the boundary of the surface. Is there a way to see that picture?
Yeah, sorry. So in the Roberts formulation, I mean, so in the sort of Roberts formulation, okay, so let's start with like a standard handle body in R3. Now what I'm going to do is, forgive the color switcheroo. Now what I'm going to do is I'm going to draw a two handle that, maybe in red. I'll draw the attaching circle of a two handle we want to attach. I don't know, something like this. You may also allow links in the boundary of that. So this is now representing a three manifold with boundary. You may also have a link in that What can I do? So here's a link in the boundary of that three manifold. So now what Justin Roberts would tell us to do is we have this through degree 0 projector. And we have a Kirby being fed through it. Oh, sorry, it's, yeah, there's two of these. We have a Kirby guy being fed through it. And maybe something like this. Okay, so it's maybe not so interesting. Yeah, forgive, I didn't draw the right picture. But so the Justin Roberts picture does support like links in the boundary as well. You just have to embed.
I just mean like how do you turn that picture into the picture that you started with? Where you have like a crossing list.
Oh yeah. Well, so this is a picture drawn in a handle body. If you do surgery on, well, okay, so if you so look at the surface. If you do surgery on that little red curve, you get a sphere, and that's the sphere. That's the 0 handle. I'm not sure. Maybe I'm not understanding the question right. I'm sorry. Okay.
So you start with a 0 handle, and then you do like the red curve, and then you.
Yeah. So these red curves are meant to be the co-cores of the one handles in my pictures. So Yeah, over people want to eat lunch. No problem. Okay. All right. Thank you.